All right, so we're going to start our keynote speech in a couple minutes, and so I'm going to do an opening introduction to introduce Andrei Klishin. Okay. Andrei Klishin is an IYPT enthusiast since late 2009 when he solved his first problem doing experiments about cutting ice with a piece of wire on the balcony of his home in Minsk, Belarus. His team then went on to win the Belarusian YPT in 2010. Andrei chose to attend IPHO instead and earned a gold medal in Zagreb in 2010. He then started his college studies in a Belarusian state university while simultaneously teaching high school physics electives and supervising the YPT team of his former school. He was a team leader of the Belarus teams at the AYPT in Austria and the IYPT in Germany in 2012. He then moved to Massachusetts Institute of Technology, from which he is getting a degree in physics and anthropology this year. Andrei is engaged with IYPT in various capacities, including his volunteer work for the IYPT archive. In 2012, he served as fundraising coordinator for the IYPT Treasury. In 2015, he has been appointed the chairman of Situation Center of the International Young Naturalists Tournament, an IYPT spin-off that follows the same format but expands the reach to younger audience and to other natural sciences, biology, chemistry, mathematics, and astronomy. Andrei is delighted to see the United States returning to the tournament and is willing to contribute to the team preparations with his knowledge and expertise. So I would love to welcome him up to give his speech.
Hello, everybody again. My name is Andrei Klishin. As I was already introduced, I represent on one side MIT, on other side IYPT, and IYPT in a sense in two different capacities. In one capacity, IYPT is this big competition that is hosted somewhere every summer, where one team from every country comes in. On the other side, IYPT is this very big educational platform which engages a ton of people across the world. Because what we are doing, actually in this room now, is not IYPT proper. It's not the big international tournament. It's a spin-off. It's kind of a variation. It's a localized version, kind of nationalized version, which IYPT as organization totally supports and wishes everybody has it. So my initial subject was how to give talks about IYPT, how to give talks about science in general, but as Jay increased my allowance in time, I would also stop on a couple of historical details, kind of where are we coming from, what is IYPT, why are we doing all this, why United States has not been participating for a bit by now. And then I'll get to actually how to craft presentations, and I hope that some advice that I can offer is very useful to you. Okay, I'll address links momentarily. So the big historical landmarks of the tournament, who are we, where are we, where do we come from? So this is a most recent map about all countries that have ever been involved in the tournament. We have about 40 nations involved total. Some of them don't exist because, as you know, the tournament started in USSR. USSR cannot participate anymore for obvious reasons. We have about 30 countries come into the tournament every year. It kind of fluctuates depending on, political issues. Like not everybody can go to Iran. So the participation in Iran in 2011 kind of dipped down and then it came back up. So here the numbers, dozens of national tournaments. Actually, we counted with my friends, and we counted 25 national tournaments that we are aware of, and that's on the high school level. And nobody said that you cannot do IYPT at university level. So there are lots of college kids trying to do this. They cannot compete directly with high schoolers, but you can make a tournament of the same format. And then we had a big debate how many people we should write there. So here's the number, it's 100,000 people, which is our kind of estimate on how many people ever participated in any stage of this tournament, including all national stages, given that selection is really big in some places. So Belarus has about 15 teams every year, and we send one team out. I would say about 10,000 people attended IYPT in some capacity as a proper international tournament, as jurors, as participants, as team leaders, and so forth. About 100,000 got involved overall. So US is marked there because US has been there for a number of times. Most of Europe is represented, Eastern Europe, Australia, New Zealand, Indonesia. We have regular 2 teams from Africa, Kenya and Nigeria. South America is only represented by Brazil, but they come in often and they're doing pretty good there. So how did this whole thing start? So Evgeny Unosov, this guy in the middle on the bottom picture, who is our founding father, he kind of invented the concept in 1979. He put in a few key values of IYPT that we hold dearly till this day. And he started the first tournament in Russia, in Moscow. It was inside USSR, kind of limited, not going international. It went international in 1988, kind of expanding to the socialist camp of the world. In 94, it started to include Western nations. In 94, the first tournament was held outside of Russia in Netherlands, and since then it's been traveling all over the place. I actively participated in the tournament between 2009 and 2012. So 1 year as team member, 2 years as team leader. Then I went to Austrian tournament with the Belarusian team. I went to international tournament, and then I came over to States, and I'm not doing it actively. I'm doing a lot of behind-the-scenes work. In 2013, Evgeny Unosov decided that IYPT kind of took off and just doing its own thing without him, so the founder is not really involved. He comes as guest of honor, shows up. But he decided to start the second tournament, Young Naturalist Tournament, IYNT, that we're preparing the third tournament this year. It is basically the same format of the physics fight, so presentation, opposition, review, except for it's aimed at different sciences. So not just physics, but also chemistry, bio, mathematics, astronomy, and so forth. And we're aiming also at younger audience, between 12 and 16-year-old, hoping to kind of start this promotion of general scientific thinking, not just limited to physics at a younger age. So we're borrowing the same format, showing that the platform is really portable. You can do all kinds of stuff with it. And we're not in any direct competition with IYPT. We're just appealing to a different group of people. And hopefully, this year, maybe in a couple of years, we will have people who did the Naturalist tournament and then graduated to the higher level to IYPT. So I'm now involved as chairman of Situation Center for IYNT, responsible for kind of outreach and propagating this idea and inviting new nations. We had like 8 teams on the first tournament, 6 teams on the second, and for the third one we have pre-registered 30. I think it's fantastic growth. It shows that the event is really popular. So some of the information that I'm going to show further about participation of US is brought to you by the IYPT Archive. That is an initiative that officially started online in 2011. It is this website, archive.iypt.org, which has a huge collection of all kinds of documents from last literally 35 years of history. It has a full list of all people who ever participated. Well, not full, like 97% of people we could identify and find, and many of them contributed documents. If you want to see how the real solutions are done by different teams, there is a solution section. And people voluntarily submit their presentations. You can look up anything from style, depth of involvement, and so forth. So you can look up the whole database of problems. Problems never repeat. So, starting with the first tournament in '88, 28 tournaments times 17 problems, you got 400 there. So if you ever need an inspiration for a physics lab or anything, go there. A lot of interesting statistics, a lot of interesting data, a lot of interesting research that people published in many journals on physics education, for example. Our IYPT Archive used to have a blog. But then we decided that we need to move to something more modern, so we changed the platform. So the updates are now on Twitter. So if somebody wants to follow at IYPT Archive, they publish new documents discovered fairly often. So I would hopefully contribute with a couple things I discovered here today. So who is it run by? So there is this guy, Ilya Marchenko, who is he's originally Russian. He participated himself in late 90s. Then he was a team leader for a while, and then he was a doctoral student in Europe, and he has been the treasurer of the tournament now. He's the founding researcher of IYPT Archive. Basically, I asked him what would be the best title to put for him. He said, well, put me as founding researcher. Basically, he is Archive. He is the only person who knows how everything runs. He really hopes that this all goes well, and on this tournament he sends you greetings from the 23rd Belarusian Young Physicist Tournament that happened a couple weeks ago in Minsk. Says hello, guides me how to make this presentation, how to make this stuff available. And he runs actually 2 Twitter accounts. One is at IYPT Archive, the other is at IYPT, just like that. So this is the list of people he follows. Scroll down to about March of last year. So you can probably notice this guy who was at it about March 2014. This guy happens to be in pretty good company of official Twitter of IYPT 2014, official Twitter of the president of the European Physical Society. So that's actually how Jay Jennings got inspiration to take somebody to this tournament to organize this whole thing. So Ilya has been very proactive in this outreach and spreading out the idea. This is a document in Russian, which is a list of participants of the 3rd International Young Physicist Tournament in 1990, which includes, interestingly, Netherlands and USA. The team of US was pre-registered by Jack Wilson, who is now Professor Emeritus at University of Massachusetts. For various reasons, the team never came in, but this was like the first indication of interest. Hans Jordens, who was pre-registering from Netherlands and later hosted the tournament in Netherlands, is now president of the International Physics Olympiad. So again, we are connected to many other big scientific events in the world. So while US did not come in 1990, we did host the tournament. We have a lot of good archive pictures. So you probably really like the fact that you have all PowerPoints. So this is how it looked back in the day. So you come in with a poster, you write something on Blackboard, you come with your overhead. You argue nothing is electronic, and everybody is dressed in this fancy, early 90s fashion. A lot of fun stuff was going on. So then US got involved thanks to our friend Don Franklin, starting first in 99. So correct me if I've been wrong on any dates, but I checked the archive section on people, so you can kind of open the section, Control F, type in USA, and see everybody who has ever went. You can localize individual participants. You can, if you want, track down where did they go further. How many of former IYPT participants went to MIT? Well, a bunch of them went. In 2005, USA was kind of at the topmost position ever reached, below Belarus. Belarus was also at the height of the glory. We never went that high again so far. We ascended to the 4th place recently. So actually the presentation, you can probably see that the color of the font on Belarusian problem is different because it's a link. Because if you open that page, you can access exactly that presentation that got 2nd place in the finals. So if you're ever interested, archive.iypt.org, fact sheets, all the information about any tournament you want. So again, as Don told us, US decided to organize their own tournament called US IYPT as a national selection. And they asked actually IYPT for the official endorsement letter, which IYPT says, well, if somebody is asking us for official documents, we can write them in any amounts, put in the signature of the president, some fancy stamp, eloquent speech, and say, yeah, we actually formally acknowledge US IYPT, and US IYPT organizes the Invitational Young Physicist Tournament, which you participated in. But soon after the selection started, United States kind of came into some disagreements with the politics of IYPT. So this is the log, the proceedings of the annual meeting of the International Olympic Committee, which is basically the governing organ of IYPT with one representative from each country after the tournament 2008 in Croatia. So Tengiz Bibilashvili, he used to be the team leader of Georgian team, and then he moved to US and he became a team leader for US team for a while. So he asked to change the number of problems down to 12 from 17. Well, IOC members didn't quite support it. And then number of 17 problems was kind of officially fixed. It used to be kind of a tradition, and then they just fixed it in the regulations that it should be 17 sharp. And yeah, a couple other minor details were fixed up. And Tengiz said that, well, under these conditions, US doesn't quite want to participate in that fashion. The reason why IYPT didn't want to accept that proposal to kind of simplify it, because we really proud ourselves on the deeply held tradition, a few core features that were invented, put in 1979, and never changed since. A lot of stuff in regulations was tweaked, so if you look, for example, at the regulations, how much time do you have to present? It changed from anywhere like 7 minutes or 5 minutes to 12 minutes now, and kind of opposition and review is very formalized these days. But they existed always, literally. So there has always been the format of physics fight, which unfortunately we are not reenacting today, but which I really hope you would go see. There are many recordings of the finals of the past years. There are many, many physics fights on videos on YouTube, anywhere. We have always had 17 problems. Nobody really knows where the number came from. Official explanation is kind of 16 is too few, 18 is too much. They were always very open-ended, very research-oriented. None of the problems literally have solutions. They go through a complicated selection process, which is kind of about as rigorous as selection for the participants. So now basically every delegation is not quite required, but very encouraged to submit a couple proposals of the problems that they want to see at the tournament that they came up with. Usually the problems, as you've seen, have the form, oh, do this and this, and you observe this effect. Explain. Build it. We don't know why it happens. Somebody somewhere might have written a paper, but the paper is not exhaustive, so there is a lot of stuff still to do. So we have about 100 proposals for the problems every year, and we select 17, and they're approved at IOC meeting after each single tournament. And we always had the structure of reporter, opponent, and reviewer, and basically this format is the core. As long as somebody is trying to do this, well, even 17 problems can change. Many national tournaments just use a subset of the problems to work on. But as long as the physics fight scheme persists, it is called the Young Physicist Tournament, and we can brand it, we can say that it's our spin-off, it's something that we invented. And many people actually really like the concept. So we kind of collect the citations of interesting people who have interesting things to say about us, like Klaus von Klissing and Herrick Schopper. I think they both visited IYPT about in '97. So Klaus von Klissing is a Nobel Prize winner in physics, so presumably he knows how science works, and he thinks that IYPT is very helpful. Herc Schopper, who was general director of CERN, the organization that runs the Large Hadron Collider in Switzerland and France, was very impressed as well, which he expressed to us in very direct terms. Last time we had in 2013 Douglas Osheroff, who is a Nobel Prize winner about 96 or 97, professor at Stanford now, who came in, he sat down in a jury, so you can effectively go present in a physics fight and be judged by a Nobel Prize winner, which doesn't happen too often. And that guy would actually listen to you and maybe talk to you and evaluate what you're doing, and so you get very qualified judgment. So what is my personal experience with IYPT? You learn to give talks and lead discussions. Discussions are key components. So in proper physics fight, there is not just the report, but you have to talk to the opponent extensively, which today we try to model through interactions with the jury members, but actually you would be mostly talking to members of other teams. You learn how to design presentations because it's very not obvious, and you need it, everywhere. Anytime you want to ask for money, anytime you want to give a talk, always you need to design presentations. You need to give some kind of narrative structure. You need to know how to present stuff, how to organize your slides, and so forth. You learn how to do prolonged research because your projects are like a few weeks or a few months, and you just have to keep going and inventing new stuff. And you usually don't know where you're exactly going. So you're organizing fuzzy projects because you don't have like a very sharp start and end. You kind of go forward and you discover a few new ways you can go, and you have to choose. And well, honestly, anything creative that you do in this world is fuzzy because you have an inspiration and you start going and you don't know where you're going exactly. Also, you learn how to work with people who don't want to work, which is an incredible exercise in management. So many people in this world don't want to work. You have to make them, you have to properly set in incentives and so forth. So what is the difference between IYPT and our peer competition? So, for example, many people compare IYPT with IFO, International Physics Olympiad. So this is a picture from IFO 2010, featuring me, because why would I show any other picture? So I won our national Olympiad in 2010 as individual member, and I won our national tournament in 2010 as team member. And they only said, well, you can only go to international one of them. Pick your choice. So I chose to go to IFO then, and I only returned to IYPT proper as a team leader later. So what is the benefits of IFO, just comparing against the same list? So instead of giving talks and leading discussions, you crunch mathematics, you draw something, you learn to derive stuff. You're not designing presentations, you're designing derivations, which can be useful. I mean, sometimes you want to write down a theory, and if you're designing presentations all the time, sometimes you take a stack of paper, take a pencil, and go until you discover something yourself. Instead of doing something over a course of a few months, the longest concentration that IFO actually takes from you is 5 hours. IFO is 2 exams, 5 hours long each, theory and experiment. So you dive in, you need to be completely focused for 5 hours, which in IYPT doesn't quite happen. You have a lot of kind of downtime and breaks and so forth. So it's kind of working on a very different time scale, and it's much more like exam taking. And the problems that you have, they do have solutions. And in terms of collaboration, you learn to work with, you don't learn to work with people. IFO is individual competition. If you know how to crunch math, you crunch math. And you go with your team members, and at most, you can chat about the problems later on. But it's questionably useful because by the time you can talk to them, it doesn't really matter anymore. So next layer that I'm involved with is the International Young Naturalist Tournament. It's our spin-off. As I said, 17 problems, still 17. We are holding on to the number in physics, biology, the scientists, participants of younger age. I'm chairman of the Situation Center. I'm learning the very different organizational side of things. So I've been already a juror, I've been a participant, I've been a team leader, now I'm trying to learn how to be an organizer. How to create a stable organization that can kind of run itself, that can sustain loss of essential members out of nothing. Just somebody has an idea, oh, let's organize a competition. You don't have any basis for it, and you're just trying to make it happen. I learned a lot how to outreach to the world. I have just this huge list of physics teachers, biology teachers, chemistry teachers, all kinds of administrators from all over the world, and we need to build a participation again out of nothing. So if you want to keep going with IYPT or keep learning how to organize stuff, I would seriously suggest you try to continue in some organizational capacity doing this. So with that I would finish the historical section and I would get to the actually question of giving talks. So here's kind of my short observation. How do people give talks? Which I've seen more or less the structure in most of your presentations. So you state a problem, you say, okay, we have this device, okay, we have this theoretical model, we did lots of experiments, it was good, they kind of compare, we have some slide which is called conclusions, we have slides that is called references. What is often not in place is understanding why each of those components need to be there. So I want to really get into the question why each of those components should be there and what is the unifying organizing principle following which you can design presentations and fit them to a particular purpose. So of course you need to start with a problem statement, verbatim, the way it's given to you by the problem sheet. The wording is very carefully checked many times, so that's exactly the way we want to see it. Then you have some experimental setup because, well, many people want to say, oh, we built a really great thing. We want to show you how kind of great it is. We worked so hard. We built this really cool thing. Then people, instead of showing a theoretical model, they start crunching mathematics, and there are awfully many presentations by people who are kind of very good at math and very good at playing with computers and not quite as good at presenting their stuff. But they know, oh, math is kind of really cool, and we know this fancy function names, which I would stop on a bit later, and doesn't quite help to explain what you're doing. We did lots of experiments because, well, our theoretical model says that there are 4 parameters that influence the phenomenon, so we kind of wiggled all of them around and showed you something, and, well, we varied all 4. What else can you ask for? So how do you compare theory and experiment? That's also often kind of a strange comparison because our plots bend in the same direction. And okay, how do you quantify that? How do you prove that your theory and experiment are actually describing the same thing? How do you prove that they actually match? Conclusion, because my team lead told me that it should be there. I'm not sure why it should be there. References, because everybody will so kill me if I don't have this slide. I'm not sure why it should be there, but they would kill me anyway. So let's just try to think, okay, let's start blank. What do you want to say with your talk? I want to say I want to put in some very simple core idea. You gave me a problem, I solved it. Here is how. You want to deliver the message that you solved the problem that you were stated. It's not a message about how hard you worked. It's not a message how much time you spent. It's not an emphasis on kind of the process of that preparation. Emphasis is on the result. You wanted something from me, I've done it. So think about your audience that's listening to you. They want to believe you. Honestly, when I'm sitting in the jury, I want to give you as high grades as possible. I want to kind of get into your report and find everything that you actually did, everything that you actually accomplished. I mostly believe stuff that you tell me, and I mean, unless it's outrageous. There are many things that you can tell people without proving, and they will still trust you. So on that part, it's especially important that you don't make people think about kind of unnecessary stuff. Your work is to solve the problem. Your work is to do the analysis and show the conclusions, show your results. So if you're kind of making the jury members, making your audience try to analyze whatever your data was, that's not what they're supposed to be doing. It's not their job. It's your job. It's something that you did back home, and now you want to report the results. So this would kind of reverberate through a couple other of my pieces of advice. And also, whenever people are sitting in talks, anybody who has seen, more than a dozen scientific talks in their life, they always wish that the speaker were more energetic, that they were more active. Maybe I'm not doing a great job right now. Sorry, I had insufficient amount of sleep the last few nights. But you can always go more energetic. You can always go more active. In that sense, if you think that your work kind of sucks, sometimes internally you have this feeling that it kind of sucks. If you're confident about it, if you just keep bashing through, it gives really great effect. Often putting a bit more effort into presentation, into the design, and to putting together your voice, putting together kind of affirmative, nice sentences, sometimes can give you better results than trying to tweak your plots a bit more, trying to get a bit more data. So how do we craft that argument? How do you convince the people that you actually solved the problems that you had? So you need to make a talk about physics, that I would kind of go from very general argument structure into how do you do it specifically in physics, and then how do you become proud of the right things. It's not a question of what you do during your preparation, it's a question of what do you accent in your presentation. So this is a typical outline how you can present a problem which kind of closely mirrors the thing I presented in the very beginning. Is that, we saw some problem, we make a claim that it's explained with this theory. That's a very important step. That you don't start saying, we kind of started building this setup, and then we kind of started looking appropriate references, because the way you present your solution actually doesn't match the chronological sequence of how you prepared it. You don't necessarily at first say the things that you discovered at first. What you want to deliver with your talk is that I solved this problem. You gave me a question, here is the answer. And I think it's very important to kind of explicitly give this claim that I think that the problem is explained with this theory. And then you go around trying to support it. But basically, before you have a claim, before you have a substance that you want to support, it's kind of very hard to guide your listeners through, because that means that you're making them work. You are making them you're making them try to reconstruct your thesis out of your arguments, which is not really the good way to go about it. It's hard to try to reconstruct an argument. It's hard to kind of get at what you're trying to say if you're saying it circumventively. So we think this problem is explained with this theory. And then, okay, how do we support it? First, we made a setup that's really appropriate. Problem asked us to do something. Maybe we put a little spin on it. Maybe we reinterpreted it. We built a setup that is really appropriate, that we think is really good to explore whatever we want to explore. Then we suggest this theory, this kind of analytical explanation, maybe something mathematical, maybe something in computer simulations. Then we made a bunch of experiments in order to confirm this theory. And then we make a careful fitting, careful comparison. And they say, oh yeah, they actually fit. Oh, conclusion? Yeah, we just made that claim, 10 minutes ago, and now we proved it. And you kind of make the point first, go around the arc of proving it, and then bring it home, saying, oh, you asked me to solve the problem. I did it. That's exactly the same message that you want to deliver. So then comes a question, during talking about your theory, about your experiment, about your apparatus, what you should be proud of, what you should accent as kind of the high points of your report. So we know that doing scientific work is really hard. I've been taught by one of my professors at MIT how do respected physicists, respected scientists can kind of blame each other and accuse each other. So, he's a respected professor, he comes to a conference in his subject, and he meets a bunch of people, and he knows what they're doing, and inside he thinks, oh, these guys are doing a really good job, and these guys are not really doing a good job. They can't show me anything, they got paid money and they didn't produce anything. So I feel like I want to express this. How do I actually do this? Because he's a scientist, he's a very polite person. So you can't really say aloud that these guys are doing bad work. So he invented a fantastic phrase that he uses instead. He says, oh, those guys, yeah, I know them. They're working really hard. You can also say they're really nice people. Because if somebody actually achieved something worthy, then you say, hey, have you seen that device they built? Have you seen those plots they showed? Have you seen that series that describes everything that they invented? You're stressing the achievement. You're stressing the conclusion of their work. You're not stressing kind of the amount of effort you put in. And you should be doing the same thing in your presentation. Making good conclusions out of your work is much harder than crunching your apparatus. You should do the first part. You should put the emphasis on the first part, on doing really good work while you're preparing, while you're sitting at home in your lab, making apparatuses, trying to figure something out. When you're giving a talk, you don't want to talk about, your hard, long hours in the lab. Everybody has long, hard hours in the lab. When you go to the competition, everybody spent a lot of hours trying to solve that problem, but somebody did it better and somebody did it worse. And what you want to say is that you did it better. Why? Because your conclusion is better than the conclusion of other teams. So that is the conclusion that you want to be making. Then another point, so this is a sample article. Yeah, this is lorem ipsum. But what I want to point out there add a few different elements that, I'm reading the first article, I'm reading the second article. What does jump in my eye? The first one says, new, invention, discovering new, with something, great, we innovated, we invented something, The second says, yeah, it says that there is something new, there is some innovation. And we're citing those guys, and we accelerated something to 280 miles per hour. I'm not sure what that means, but that's a number. That's an achievement. That's a statement of the result. So you didn't really invent absolutely everything that you're talking in your presentation. That's not how science works. One of the chief organizational principles of science is, standing on the shoulders of giants. There are people who investigated the same problem before you. You should acknowledge that, and you should try to build on top of it. Basically, if you ever say that, you're doing the paradigm-shifting, groundbreaking work, and everything before you was wrong, then most people would be very skeptical. Like, you didn't really invent all of it. Even if you're proving that somebody's theory is wrong, it was done before you. You're basing on the conclusions of those people. Maybe it is indeed wrong, maybe you can make an argument, but you are still referencing them. The style of presentation or the style of articles that you see on the right, when you're citing people and when you're presenting some kind of numerical evidence, some kind of real facts why your work is actually new, that actually looks much better. And you know what? People would not read those references. You all showed references that, oh, we cite this and this articles. You know what? I will never read that. But you show me those articles and I believe you. Audience generally believes what you say. If you say that you read those articles and you picked up some ideas from them, unless by miracle chance I have actually read that, and there are a lot of articles in this world. I haven't read anything really about the problems of 2015. If you're saying that you're citing somebody with, roughly relevant titles of articles and roughly relevant kind of scale of the journal that published it, and I know that, oh, if it's like physical review letters, yeah, it's a very good peer-reviewed journal. I trust most of stuff that's written there. I would acknowledge it. I would think it's really serious. At the same time, you don't downplay your results. So the way to make yourself look really good in terms of your contribution, you play on contrast. You don't say that you invented everything, and you don't say that you're just repeating the work of other people. You say, oh, here is what existed before us. Here is what existed before us, and here is what exists after us. We made this difference, and this contrast is really visible. This is something to be stressed. So then I want to go over a couple kind of generalizations of explanation tricks, which can be very useful for presentations. How do you explain a complicated concept? So one big issue, which I saw in a number of your slides, is perception of many objects. Somebody like a big psychologist can tell you, oh, human brain cannot process more than 1, 2, 3, 4, like 7 objects at the same time. Yeah, that's true. So maybe your theory is really complicated. It has really a lot of steps, really a lot of things going on, but you can't perceive more than 7 objects, or whatever that number is. But the complexity of your presentation doesn't quite correlate with complexity of your actual theory. What you're doing on the stage is you're being a performer. You're not reading off script. What I'm doing now is a speech. It wouldn't work the same way if I wrote down the text of everything I have to say and just handed it out to you. You're a performer. You're trying to convince people to take your viewpoint. You're trying to convince them that you did something really good. You want them to understand your theory. The way you get good grades at IYPT is if jury understands what you did and opponent understands what you did, and they think you actually did something useful. If they don't understand what you did, even if it's kind of great, you think so, grades go down. So you should design your slides, you should design your talk in such a way that you make them see what you want them to see. So as an example, I'm borrowing some plots from my own work from like undergrad labs at MIT. So I had this experiment. I was measuring the decay of muons, elementary particles that come to us from space. I have this kind of huge machine, a big chunk of plastic, and muon comes in and decelerates and almost stops in the middle of my hunk of plastic, and then after some time it decays. And the moment it stops, it emits a flash of light that I can detect, and when it decays, it emits another flash of light I can detect. And I'm trying to measure what is the time between those. That time is random. I'm trying to figure out what is, on average, the decay time. And I leave it standing overnight collecting data. It detects like 1 event per second. I leave it for 10 hours. Then I build a histogram of how many times I detected each of different decay times. I get something like this, and I show you this plot, and you're like, what am I supposed to find here? If you just show that plot to your audience, they would be trying to analyze it, and basically they would be trying to do your work, which they should never be trying to do. So let's try to think how to make this plot better. Yeah, the data is correct. The data is useful so that you can extract something from it. On this version of plot, you didn't extract anything out of it. It's raw. On the next plot, however, well, what do we see here? I just added a couple elements. I added legend, I added some kind of trend line, I added a bunch of numbers. So I see one line, something centralized through all of those points, which kind of epitomizes the trend that I have, that, more often than not, I see small decay times, and very rarely I see large decay times. And well, if I have this like fuzzy red background and I see very clear thin blue line, my eye is attracted to the thin blue line because it's a very simple object. Perceiving one line as opposed to 1,000 points is very easy. So we say, oh, okay, so there is a trend. So in the backdrop of their data, I see a conclusion of their data. And then at the same time, I see a numerical conclusion of their data. I see some kind of numbers that I extracted from here with uncertainty. So like chi-square, degrees of freedom, probability, it's like statistical parameters of this extraction. So I'm given the decay time is this with this uncertainty. So what happens, how does this trick work? So I gloss over the data. I kind of show it to you, but I kind of don't put much attention to any single of those points. Any single individual point on that plot is not important. Nobody cares about any single point. If I deleted my aggregate conclusion would be exactly the same from all the rest points. I thin down the data. Instead of trying to explain to you what every single point means, I just show you the trend. Looking at the trend is much easier. I saw a number of you presented these huge tables with lots of numbers and so forth. And if I see a table with a lot of numbers, I think, wow, they're working really hard. They're trying to show me something. And I cannot add and multiply and subtract and so forth. I cannot analyze all those points while I'm trying to actually listen to you. You don't want people doing that. So show plots with trends. And you know what? Use skip analysis. I showed you that plot. I say, OK, I just draw a line through the center. I put you some kind of number. I didn't tell you how I'm doing this. Yeah, there is kind of complicated mathematical apparatus that actually calculates where the trend line should be, what the parameters should be. I didn't tell you this. And you know what? You don't have that question. You don't really think that I should have showed you this, because presumably those methods are kind of standardized, and presumably you did the right thing, but you're showing me the conclusions, and conclusions is what I care about. Conclusion is what you should be proud of. Again, being proud of the right things. So another description of exactly the same experiment. So I have this plastic scintillator, that hunk of plastic which stops muons, and then various kind of signals go out of it. This is like an electronic chain which I use to measure stuff. So muons come in, I detect about 0.35 counts per second. These PMTs emit little 3 nanosecond pulses that go into the next thing, constant fraction discriminator, that if the pulse is stronger than certain amplitude, it emits control signal 100 nanoseconds. Two pulses go into coincidence circuit, which emits the next signal if they come at the same time, and doesn't emit anything if they don't come at the same time, and so forth. So another example. I'm trying to measure a thing called fine structure splitting. So in atoms of sodium, there are 2 energy levels that are very, very close to each other. And atom can transition to one of those energy levels or to another from something that's far. And it produces 2 different emission lines, which are very close to each other. But you can distinguish them. You can measure that. So I'm running this thing. I'm trying to measure what is the intensity of light emitted by a sodium lamp at different frequencies with this very, very precise stepping. And I see this kind of 2 peaks. What do I do with it? I want to measure what is the distance between them and how does it transport into the difference of energy levels. I subtract background noise. I designate these peaks as my lambda 1 and lambda 2. I designate the difference between them as delta lambda. I show you the number again. I don't tell you how I got this number. You presumably believe that that number is correct. I show you the reference value from NIST, that's National Institute for Standards and Technology, which kind of publishes this definitive constants measured very carefully. I'm not the only one who wants to know the fine structure splitting of sodium. And I show you my value to compare it. So how did this trick work? I show you the whole scheme. I show you the whole plot right away. And then I use animations. So further elements that complicate the picture, they appear one by one. They don't appear all together. I walk you through. So animations show up in the order in which I do analysis or in the order in which a signal propagates through the chain. I use colored takeaway points. That's what they taught me at MIT. Use colored takeaway points. Color makes so much sense. You show this thing is kind of pink, this thing is kind of red, this thing is kind of blue, and I understand, oh, those are some kind of different functions. They stress slightly different things. This is a purely visual thing. This has nothing to do with physics. This has nothing to do with, what color that line actually is. But it kind of stresses very quickly different concepts. And I know that I'm not trying to tell you the same thing over and over again. I'm telling you something different. And actually, with all that analysis, I'm showing you new information. I showed you the whole chain, and then I started telling you how long are different pulses created in different parts of the chain, which is important for the analysis of the chain, but which is new information which wasn't originally present on the scheme. And the last trick is when I'm trying to show you two things that I want to contrast against each other on a plot. So again, I'm measuring this specific emission lines in hydrogen. So I have one kind of transition which generates this very intense line. So I have this very, very high peak that is very easily visible against the background noise. And then another transition is much more weak. I have this very, very subtle peak. So on the left, the ratio of intensity of the emission line to the background is about 1,000. On the right, it's about like 1.6. So the right one is barely visible, and the left one is very tall. In another experiment, I was testing experimentally the special relativity time dilation, so that for objects that are moving really fast, the time flows slower. So the same muons, they should be decaying in like a couple microseconds. But because they're moving really close to the speed of light, if you're trying to measure their decay time from our reference frame, it takes them really a lot of time to decay, so that it can actually be born in the upper layers of atmosphere and come all the way to here without decaying in the process. And we can make this plot about how fast, so what is the flight time from upper atmosphere to here as measured by the internal clock of the muon, as opposed to the speed at which they're moving. So we find this threshold that they need to be moving at least this fast so that we can actually detect them, so that they don't decay before they reach us. So only muons from that level reach us. So what again is the trick? What is the big presentation technique that unites those two pieces of analysis? I broke the slide into two halves. In one case, I'm showing you two plots next to each other. In other case, I'm showing you a scheme and a plot. And each half has a few objects that I can kind of independently perceive, but only both of them together make sense. So I'm not trying to make you make sense of too many objects at the same time, because you can say, oh, let me just care for a second about the left half. Oh, yeah, that's reasonable. I can actually understand what's happening. Okay, let me forget about it and think about the right. Okay, this also makes sense. Oh, so now what is the commonality? How do these halves play with each other? And you discover that. Then I have this section on how to present mathematics. As I said, there are teams that are really fond of really complicated mathematics and really stressing out how they built this really cool model. So once upon a time, I was watching this presentation in which they needed to calculate a magnetic field. How is magnetic field distributed in space? And they were saying to me, oh, so we use this fundamental Biot-Savart law, and then we replace this finite magnet with kind of a continuous magnet in all space that is Heaviside function in space, important Heaviside, a very important phrase. And then we Fourier transform it, and then we integrate something in Fourier space, and then we use Bessel functions because it's a really cool name, you know, Bessel functions. We are smart, we know what we're talking about. Then we Fourier transform back, and then we finally plot something. And so this is what you start with. You start with Biot-Savart law, and you end with plotting something. Whatever is in between is you're being proud of yourself. You're being proud of working really hard. But your talk is about physics. Your talk is not about how to calculate magnetic fields. My talk is about how to give some more complicated conclusion in which is intermediate step. Yes, I need to calculate that magnetic field. You don't need to know Bessel functions. You don't need to know Heaviside functions. Skip that. You say, I just started with this premise and I reached that conclusion. I know, yeah, somewhere along the way you integrated something, and you know there are not too many ways to integrate things, and there are not many ways to make errors on the way. So disregard it. I believe you. Yes, you show me the field, the magnetic field distribution, and yeah, it kind of makes sense. So I will not ask you how you calculated it. I will just trust your word. So the next interesting concept, and I promise I don't have too much left, is how do you report your results and how do you report uncertainties? And we had a couple discussions where do you have error bars and where you don't have error bars. So again, in the same physics lab in MIT, I was working with my partner, and we were measuring some fundamental constants in our experiment. So I was trying to measure this is my partner. She was trying to measure the electron charge. And so on the left is the value for the electron charge, fundamental charge that she got from her experiment with an estimate of the uncertainty, and on the right is a kind of established value, the standard one that's measured very carefully by many people. So the thing on the right we can totally trust. The thing on the left, can we trust the thing on the left? Any opinion? Is it a good measurement by any chance? Yeah, I know that I'm trying to measure something that already exists, but am I close? Well, is my partner close to that? What do you think? How do you evaluate whether that's a good result? Any opinion? So the result is 1.21. The actual value is 1.6, so discrepancy is what, 0.4. The uncertainty standard deviation is 0.25, but, well, standard deviation uncertainty doesn't mean that the result necessarily fits in that bracket. It fits there with probability like 95%, depending on how precise you want to be, 97, 99%, whatever. There is some kind of miniature chance that it's far outside. So I'm less than 2 standard deviations away from the values that I wanted to get. Well, that's kind of okay, actually. It's not terribly great, it's not terribly close, but it's kind of okay. But then just to compare this to another result, I was measuring in my experience the Boltzmann constant. So on the right is the Boltzmann constant, 1.38 times 10 to minus 20 joules per Kelvin. And on the left is the values that I got in my experiment. I tried as hard as I could to make analysis. Yeah, probably something was not quite great in my data. I'm being very precise. I checked every single digit that I'm showing to you. Is this a good result? What do you think? So it's like 2, the first digit is 2, there the first digit is 1, and it looks like my uncertainty is about like 25%. Yeah, so, no, not 25, 2.5%. But then if you kind of look carefully, that order of magnitude is the same, 10 to minus 23rd, but the value that I measured is somehow, 20 times larger than the established value? That's kind of not good. And my uncertainty is not several orders of magnitude back and forth. My uncertainty is 2%. So I measured something that is 20 times bigger than it should be, and I claim that uncertainty is very small. So I'm ending up really far from this result that is presumed to be correct. That probably means that I screwed up. So uncertainties actually tell if your argument succeeds or fails. If I just give you the numbers, if I said, oh, we measured 1.21 against 1.6, is this good or not good? If you don't know what your uncertainty is, you can't truly gauge. If you know what your uncertainty is and you know what your discrepancy is with the theory, then you can kind of gauge, is it good, is it not good? Often your theory would give you a prediction that's kind of an exact number, and your experiment would give you some other value with an uncertainty margin. So if theory and experiment match with an uncertainty, then you're good, then you're fit. If they don't match, then you need to work more on it. So this uncertainty estimation is really crucial to say that your theory works or it doesn't. So what do you say in the conclusion slide? I'm not trying to be surprising in the conclusion slide. You're not trying to make something new. I've seen in one of the presentations it was like, oh, so this is conclusions, and then we just keep on deriving stuff. And after the conclusion slide, you don't keep deriving anything. You should make a claim in the very beginning. I think that this effect is described by this theory. Conclusions, oh, it is actually described by this theory. You're repeating, in a sense, exactly the same stuff that you claimed in the beginning. In the beginning, you didn't have any support for it because it takes like 10 minutes to build the support for it. And in the end, you say, oh, it's actually true. And I look at it and think, oh, yeah, that's actually true. Well, they did a great job. So how much of it, how fast you should be talking? So I've been talking, according to my clock, for 58 minutes already. Maybe you're really bored. This is slide number 41, so this puts me at about 1.5 slides per minute. No, 1.5 minutes per slide. The standard in like proper academic world and in IYPT is slightly different. IYPT, you have this 12-minute talks and you've done a really big project probably. And so people are cramming information like crazy. I've seen presentations doing like 20, 30, 40 slides in 12 minutes. Imagine if I just tried to tell you all of this in 12 minutes. That would be crazy. I would also, run out of breath and so forth. Preparing presentations is a lot about how to cut out stuff, how to not show unnecessary details, how to not overcomplicate the job of the jury members, how to not overcomplicate the job of the jury members. I just show you a bunch of tricks at how you can do this. So you're trying to make the experience of people listening to the talk very kind of streamlined. In IYPT, because you have to cram in time, you can do like 1-2 slides per minute. So a typical talk would be in 12 minutes like 20, 25 slides. Beyond that, it's not possible. And like you can only do it if it's well rehearsed, if you exactly know what you're talking about at every moment. If you don't quite know, then you should allow yourself more time. A couple of common courtesies that people use and that really helps to kind of perceive what was happening is to insert section delimiters, give an outline of your talk, because especially if it's many slides, you should kind of break it into a few pieces. So I told you I'm going to talk about history, and then I'm going to talk about presentations. Put in slide numbers. Many like PowerPoint styles do it automatically for you, so you can see this is slide number 42. So that it's much faster in discussion if you don't say, oh, can you go to that slide, with that formula? Instead you say, oh, can you go to slide number 12? And people just cycle to slide number 12. Very streamlined. It's kind of a courtesy. It doesn't add too much to your argument. It's just kind of being polite. And then last little bit that I want to talk about is how to critique a presentation. It's something that we didn't really do now, and the jury members didn't present a systematic critique. We kind of just attacked a couple of your points, but didn't try to, our goal was not to ruin your report. It was to kind of assess a little few points. In proper IYPT, your goal can be actually to ruin somebody's report. So how do you do that? You need to decide whether you like the talk or you didn't like the talk. So, they're presenting an argument, something like this. Maybe in this shape, maybe in some other shape that, you observe some effect because the problem says so, and, we tried it, we actually observed this effect, made up some kind of setup, some kind of theory, some kind of experiment, it kind of fits together, here's our conclusion. And then you can start poking holes at it, like, is your setup adequate? Like, did you try everything? Can you measure actually the quantities that you actually need to measure? Did you do correct assumptions for theory? Did you leave out something very important, or did you actually fit everything in? Are uncertainties correct in the experiment? You can ask people about error bars. I thought it's a shameful question. I thought that error bars, should be there because people would yell at me if they're not there. I learned that error bars are crucial. If somebody shows you that their uncertainties are really screwed up and that their theory and experiment are really far, and you can point that out, you can say, well, you just gave me a piece of abstract mathematics that doesn't relate to the real world. So that's not good. Is the convergence reasonable? That's exactly what you're trying to test. And then are the arguments sufficient to justify the conclusion? Maybe they wrote a theory for some really special application. And yeah, they proved it works, but something more general, they're missing out. But importantly, so you can ask, which of these questions will just ruin the whole thing? Well, none of them. You play Battleship probably. No matter how much you try to hit one point on the ship, you're not going to destroy it. You need to hit all of them. If you can show that somebody's presentation has systematic flaws in here and here and here, and their theory was kind of incomplete, and they kind of screwed up on confirming it, and their setup didn't really allow them to access the regimes they're talking about, and it's insufficient to justify the conclusion, then they're going down. Then you're showing, they actually failed to deliver good results. And again, you're not trying to well, they may be saying about how they worked really hard. And you can also say, yeah, you worked really hard. It was a really nice presentation. Unfortunately, you didn't prove that you showed the problem adequately. Well, you wrap it in some more polite phrases, but that's the essence of what you're doing. And so with this, attacking physics argument is kind of the last thing you do, because I'm not telling you how to be a jury member, because you're not a jury member so far. You can learn it later with more physics. So on this, I would wrap up and say that you've been sitting in a lab for a really long time. You did really cool work. You think you did really cool work. You can tell your friends how you did really cool work. Your opponents don't know that you did really cool work and don't know that you have really good conclusions. You have to tell them. So they don't know it yet. Go tell them. And on that, that's it. Thank you for your attention. I can take questions if somebody has questions. Well, looks like nobody has questions. Oh, please. So I think to kind of simplify the preparation, well, Don has an answer.
In our organizational system, we felt that if we dropped down to 12 questions, that we could, that everybody had to do them. Where with 17, you can draw 2 refusals, so we're down to 15 anyway. And so we're saying if we went down to 12, then everybody would have to have everything prepared. And so that was the reason for the 12. But it didn't, I think the first time was in 2004 and 2006, and it never flew with anybody else, and so that's why the 17th. And I think a lot of it is the thing of USA is not a dominant power in the world of physics, okay? And this organization have already been going on. And so therefore, we would have had support from other countries before we went into the meeting.
Yeah, but we still think that we need to live in 17 problems, because so what you do inside a physics fight is kind of the tactical level. What you do between physics fights is a strategic level. If you have really many problems to choose from, and given that there is a constraint that problems cannot repeat, so in the first physics fight of IYPT, you can choose to challenge your opponents for anything you want to hear. In the last ones, you have very limited list because they kind of presented most of stuff or opposed stuff or rejected from something. So you often have to kind of devise some kind of strategy how you go about to play the problems that you want to play. If you have what we think is the optimal amount of choices, you can do more strategy. It makes the tournament richer. Yeah?
Well, as a suggestion, there would be a good rehearsal practice to present the problem to someone that doesn't know anything about physics or the problem. If they do get the main points, you know what I'm saying?
Yeah.
The clarity of the presentation and
well, sometimes you just run into a question of what should you consider common knowledge. So, if I see somebody presenting a report and they're saying, oh, in theory we're relying on Newton's laws, yeah, you maybe should cite Newton, 1600s, or any physics textbook ever. I mean, most of talks should be designed in such a way that people with general knowledge of physics, the jury members have a requirement to have a degree in physics, maybe not in the field that you're talking about.
Yeah.
If somebody with a degree in physics can understand you, then you're doing a good job. Okay. If we're done, then we're done. Thank you.